Hello guys, today in this video we are going to discuss about particle in a one-dimensional box, or we can say infinite deep potential well. As you can see in this animated picture, consider the one-dimensional motion of a particle of mass m confined between two perfectly rigid walls separated by a distance a. Small a, here you can see x equals to 0 and x equals to a are the rigid walls we are talking about. In the region between the walls, x equals to 0 and x equals to a, the potential is 0. And at the rigid walls, that is x equals to 0 and x equals to a, the potential is infinite. That means the particle is trapped inside a finite dimension. In one dimension, as you are considering x equals to 0 to x equals to a, the particle is free. So the potential is considered to be 0, and at x equals to a and x equals to 0, the potential is infinite. So the particle cannot go out of this, potential well, or the one dimensional box we said. Such a particle is said to be in one-dimensional infinite potential well or in a one-dimensional box. So here, mathematically, we define that the potential will be 0 for x lying between 0 and a, and will be infinite for x greater than equal a or x less than equal 0. Okay. So elsewhere, other than 0 to a, between 0 and a, the potential function we consider to be infinite. Since the potential is infinite outside the wall, the probability of finding the particle outside the well vanishes. So there is no existence of the particle outside the well. So psi x, the function psi x, that is the wave function which will actually represent the particle, will be 0 in this. In this means greater than equal a and less than equal 0. The wave function will not exist, right? Inside the well, if you will see, we can write the Schrodinger equation because the particle exists within a finite dimension x equals to 0 to x equals to a. So we can write the Schrodinger equation for that infinite deep potential well as d square psi by dx square plus 2me by h bar square psi is equal to 0. Here we consider the time independent Schrodinger equation for a free particle because the particle is free between 0 and a, right? So from this Schrodinger equation, further, if you want to solve it, you can write d square psi by dx square plus k square psi is equal to 0, where we wrote k square is equal to 2me by h bar square. Okay. So this is a ordinary differential, homogeneous differential equation whose general solution can be written as what? As this: a e to the power I kx plus b e to the power minus I kx. That is the linear combination of two exponential, complex exponential function, or else you can write as the combination of two sinusoidal functions like a sine kx plus b cos kx. This can be the general solution for this particular equation. You find d psi by dx and then d square psi by dx square, and then you write k square psi, substitute it, you will see that it is satisfying the above differential equation. So the general solution can be taken as psi x equals to a sine kx plus b cos kx. For simplicity, in one dimension it is not required to take the exponential function, you can also take this sine and cosine to solve it further. Okay. So we know that the wave function at x equals to 0 will not exist because the potential becomes infinite there. So when the potential function becomes infinite, the wave function will not exist. So psi x at x equals to 0 will vanish. So we can write that as 0. Substitute the value for psi x, the general solution that we wrote. So we wrote the general solution to be a sine kx plus b cos kx. okay, at x equals to 0 will be 0, right? Substituting the value of x to be 0, we can determine that b will be 0, right? Because here you substitute sine kx, x is 0, the whole thing will be 0, sine 0 will be 0, plus b cos kx, if I'll substitute x is 0, cos 0 becomes 1. So we got b is equal to 0 by substituting this. Okay. So the wave function now can be written inside the well, okay, inside that, finite dimension x equals to 0 to x equals to a. The wave function can now be written as psi x equals to a sine kx, substituting b is 0. B is 0 we determine, putting the boundary condition psi x at x equals to 0 is 0, right? Let us now see what are the energy eigenvalues. Further, putting the second boundary condition that we have considered, that psi x, the wave function at x equals to a, will also be 0. It will vanish because the potential is infinite there as well at x equals to a. So now if you will substitute the value of psi x that we determined, a sine kx at x equals to a will also be 0. Substituting the value of x as a, we can rewrite it, a sine k is equal to 0. So further we can write sine k will be 0. So sine k can be written as sine n pi, where n can be 1, 2, 3 and all. So we can write it as k is equal to n pi, where n is 1, 2, 3 and all. So here, why didn't we take n is equal to 0? N equals to 0 will also satisfy the equation sine k is equal to 0. But as you can see, ka cannot be 0. If I'll write sine k is 0, if I'll write this, then ka will also give you 0, which is not possible because k is 2 pi by lambda, which is a non-zero quantity, and a, which is the finite dimension we said, cannot be 0, right? So we excluded n equals to 0 here, as both k and a are non-zero quantities. Okay, so we considered n from 1, 2, 3 and so on. So here this is important, we got ka is equal to n pi, right? Further, if you will substitute, k is 2 pi by lambda. So 2 pi by lambda times a is equal to n pi. Then you can find out what is the value of a. So a you can write as n lambda by 2, right? So a is equal to n lambda by 2 clearly indicates that allowed bound states are possible for those energies for which the width of the potential well, which is A, is equal to integral multiples of half wavelength n times lambda by 2, where n is 1, 2, 3. So you restricted the values of A. So A can be lambda by 2, 2 lambda by 2, 3 lambda by 2, this, right? So there are allowed bound states possible, okay, for those energies for which the width of the potential well is equal to the integral multiples of half of wavelength. So this is important. A is equal to n lambda by 2, which we will use further. Okay. So now we have k square is equal to 2me by h bar square. This is what we initially took to write the general solution for the Schrodinger equation, time independent equation. So now here, whatever value we got for Ka, which is like n pi, we got K is n pi. So if I'll multiply a square to both the sides, we can write this. Then Ka is equal to actually your n pi. So we can write it as n square pi square is equal to this 2me a square by h bar square. Then we can solve it for E and write what is the value of E. So E is h bar square pi square divided by 2m a square n square. So in general, if you want to write, you can write En is equal to h bar square pi square divided by 2m a square. N is equal to 1, 2, 3 and all so on. You can write accordingly. You can write what is the energy values, like for ground state and next excited state, further next excited state, all these values can be written. And you can see, okay, these are energy eigenvalues. So thus the energy of the particle in the infinite potential well is quantized. You can see that En is proportional to n square, right? And n varies. So n cannot take any random values. N has to be like 1, then you got E equal to E1, then 2, you got E2. So likewise. So the ground state energy here, the minimum energy is what? H bar square pi square divided by 2ma square by substituting n is equal to 1, and we call it the ground state energy, right? That is the minimum energy of the particle and is called the 0 point energy. Okay, so what we got here, En, if you will write this to be E1, this h bar square pi square divided by 2ma square, if you will consider this to be E1, then we can write En is equal to E1 times n square, right? So the energy of the higher allowed levels are all multiples of E1 and are proportional to the square of natural numbers, because you said n equals to 1, 2, 3 and so on. The value of energy lying between the allowed energy values are forbidden. So you cannot take any random values. Okay, either you will get like, E1 n square. So E1 first one, then 4 times E1, then 9 times E1. So that way you will get all these multiples, right? The energy levels are not equispaced. Energy levels are not equispaced. What do you mean by this? The spacing between two successive levels increases with increase of n. This is what this particular relationship gives. En equals to E1 n square. So first you got 1 square times E1, that is your E1 energy level. Then 2 square times E1, that gives you the next E2, which is 4 times E1. 9 times E3 will be 9 times E1. So you can see that these energy levels, if you consider, they are not equispaced. Okay, the integer n is called the quantum number here. Okay, the integer n that we said, n equals to 1, 2, 3, this is known as the quantum number. Okay, each value of n corresponds to one allowed energy state of the system, just like we said E1 and E2 is 4 times E1. So these are the allowed values of energies. Okay, fine. Let us now see, once we got the eigen energy values, that is the allowed energy values, we need to know what is the allowed wave function, right? What is the wave function? We will see, or we can call those eigen functions. Okay, so we know mod psi square is the probability density, as we are considering one dimension, right? If you will write the probability density in dx and integrate over the range of dx, here as you can see, minus infinite to plus infinite, mod psi square dx is equal to 1. So this says that the total probability of finding the particle, if the particle exists, will be 1, right? So now here, since the wave function is non-zero, only in a particular region given by x is equal to 0 to x equals to a, right, we can rewrite the value that we have already obtained for the wave function from the general solution, if you remember. So b is equal to 0 and we wrote only in terms of a sine kx. So mod psi square, if you write mod psi square, you can see that mod a square sine square kx dx, this way we can write. So the wave function that we have obtained here, we have not taken any complex exponential function, so you can just multiply like a sine kx into a sine kx. If it is a complex exponential function, you need to multiply with its conjugate, right, psi star, to get the mod psi square. So here you have taken only the trigonometric function, so you can write mod a square sine square kx dx is equal to 1 integrated between 0 and a, as the particle is existing or is there in a confined region of 0 and a. So further you can like integrate it, sine square kx, you can write it as 1 minus cos 2 kx by 2, and then integrate it. Mod a square is constant, you took it out, and then 0 to a. Sine square kx we wrote as 1 minus cos 2 kx, which will give you 2 sine square kx divided by 2 will give you sine square kx dx is equal to 1. Solve it further. So taking this 2 or 2 by mod a square, you can write integrated just x integrated from 0 to a, and this cos 2kx by 2 can be written as sin 2kx by 2k, limit 0 to a. So by solving this, we can write 2 by mod a square is equal to a, right? Here we substituted the limit sin 2k. When you substitute a, you can write that that is k is equal to n pi, so you can write it as sin 2 n pi, which is 0, right? So from that we got 2 by mod a square is equal to a. So further you can solve it for mod a square, which is 2 by a, and then you can write a is equal to square root of 2 by a. So in the wave function psi x is equal to a sin kx, we got the value of a. We solved the value of a from the probability density. Okay, mod psi square dx integrated over minus infinity to infinity is equal to 1. Using that, we got the value of a, right? So the normalized eigenfunctions we can write, okay, as the general wave function can be written as psi n is equal to square root of 2 by a sin kx, or you can write sin root over of 2 by a sin k is n pi by ax. So substitute for n is equal to 1, n is equal to 2. So for all for all values of n, you can write the wave functions, right? So n is here the quantum number. For each quantum number, you can write the wave functions accordingly. Okay, same way, if you want to write the general probability densities, mod psi n square gives you the probability density, that is the probability of finding the particle in a particular volume, that is given by 2 by a sine square n pi by a x, right? Just writing it as psi n mod square is nothing but psi n multiplied with psi n star, the complex conjugate. If you are writing a complex function, here you can simply multiply this psi n and psi n, because there is no complex function here we considered, right? Okay, so after this, let us represent the wave function. Actually, for every state, what is the wave function? Now you can see in this diagram, at x is equal to 0, we have the potential is infinite. At x equals to a, the potential was infinite. So here, after x equals to a onwards and below x equals to 0, okay, we got the wave function becomes 0, vanishes. It doesn't represent anything, because the potential is infinite here, so we cannot say that the wave function exists here. But here within this range, in this range, you can see the potential will be non-zero. The wave function sorry, potential is 0, so the wave function exists here, that we said. So now if you will represent these particular states, okay, so what will happen, like what will be the states, what is the wave function, how the wave function looks like. Okay, further you can see what we did here. We derived that a is equal to n lambda by 2. So if you'll substitute n equals to 1, then we got a is equal to lambda by 2. So you can write lambda equals to 2a. So lambda equals to 2a. So whatever wave function you are writing, wave function, if you are writing psi 1 is the wave function for n equals to 1, for n equals to 1, then its lambda value, its wavelength value must be what? 2a, right? So this way we can see, I can write psi 1 x is equal to root over 2 by a sine pi by a x. You can see this is my lambda value, and this lambda value represents 2a. Here you got lambda by 2 is equal to 0 to a, so lambda is equal to 2a. Similarly, for n is equal to 2, if I will substitute here 2 times lambda by 2, so I got a is equal to lambda. So the second wave function will be like this. Second wave function will be root over 2 by a sine 2 pi by a x, and you can see psi 2x represents the whole lambda here. Okay, so a is equal to lambda. A is the dimension here. A is equal to lambda, right? So this is what we got. Similarly, if you want to write psi 3, the third wave function, it looks like this. N equals to 3, you got a is equal to 3 lambda by 2. So lambda is equal to 2a by 3. So 2a by 3 you can see over here. Psi 3 is root over 2 by a sine 3 pi by a x. So these are, this way you can write all the generalized wave functions for different states, n equals to 1, n equals to 3, and so on, right? Okay, so finally we can talk about the probability density. We know that the probability density is a real quantity. Wave function is a complex function. Okay, like it has no physical significance, but psi n mod square, if you are writing, you are talking about the probability density. It's a real quantity. So in this case, we can just write psi n into psi n, as you have not considered the complex function. So 2 by a sine square n pi by ax, that is your psi n mod square. Okay, so now here you can see what is the wave function. We are trying to compare the wave function and the probability density for each wave function, right? So you can see psi 1, then what will happen to psi 1 mod square, psi 2, what will happen to psi 2 mod square, psi 3, and what will happen to psi 3 mod square. You have the generalized function, I mean probability density written over here. Probability density gives you the probability of finding the particle in a particular state, okay, per unit volume, or here it is one dimension, so per unit length, right? Okay, so now you can see if this is your psi 1, where we got, lambda is equal to 2a here, lambda is equal to 2a psi 1, right? Then the probability density will be like this, psi 1 mod square. Only here the change is the amplitude. You can see, like, you got 2 by a, right, and sine square n pi by x, so definitely the amplitude will be more, but it is all positive. Here it was positive, here also you got positive. Psi 2, you can see, like, you have positive and negative, you can see the extremes, right? But if I'll take psi 2 mod square, you can see psi 2 mod square, positive is squared, you got this, negative is squared, you got the same thing, right? This way. So this gives you a real quantity. There is no, I mean, a negative value, like here you can see, right? Similarly, psi 3, we got lambda is equal to 2a by 3, and here you just like you take psi 3 mod square, which is psi 3 multiplied with psi 3 star, the complex conjugate. Here we have considered only the real, so psi 3 into psi 3, right? So these are the wave function and its corresponding probability density. Okay, you all can see this. Now, finally, we consider a one-dimensional potential well or infinite deep potential well. This represents psi 1x. You can see as the particle goes and comes back, the direction of propagation, the k vector that changes. So when we took that psi is equal to a sine kx plus b cos kx, or finally, when we took a sine kx, k gives you the direction of propagation of the vector, right, of the wave. So here you can see the direction of the propagation changes continuously, and you can see what happens to psi 1x. Accordingly, the psi 1x will change, right? Same here, but the wave function gives you, for positive values we got it, only for the positive values we calculated. For the negative value minus k, you can do the same thing, and you can demonstrate how it's actually flipping. You can see that, right, for different direction. Same for psi 2x. You can see here we got lambda is equal to a, that is seen, lambda is equal to 2a here, and here we got lambda is equal to 2a by 3, and here also how the wave function varies, okay, depending upon the direction of movement of the particle from 0 to a or a to 0. Okay, so this is all about a potential box or one dimensional potential box, where a particle of mass m is actually moving freely, okay, where the potential is considered to be zero. It's a what force free, or you can say force free field. There is no other force acting on this, so potential is zero, and the potential is infinitely high at the rigid walls, x equals to 0 and x equals to a. So that way we can write for a system, such a system bounded by high potential, we came to know that the energy values are nothing but eigenvalues. That means allowed energy values are there for different states. The same way we got that the wave functions are also discrete here. Okay, they have also certain, I mean, eigen functions for different states like n equals to 1, n equals to 2, and n equals to 3. Accordingly, the probability density also varies for different states. You can see psi 1 mod square gives you a different value, psi 2 mod square gives you a different value, psi 3 mod square gives you different values. Okay, thank you for watching.